Hey robot makers, hope you're having a good day so far. So do you want to build your own Bluetooth remote control with MicroPython and Raspberry Pi Pico? Then this is the show for you. So let's dive straight in. My name is Kevin. Come with me as we build robots, bring them to life with code, and have a whole load of fun along the way. Right, let's get over to our keynote and let's get straight into it. So you might remember a couple of weeks ago, months ago, I think it was actually August last year, we created this PCB live on the stream, and about 2 weeks later we got that sent back from PCBWay, and since then I've not really written up the project of how to actually use that with a Pico. So that's what today's show is all about. So let's have a quick look at some of the features. So this, I call this GamePad 2. It's supposed to look like a game controller. So you've got your D-pad on the left-hand side. You've got some additional controls, whatever you want to use these for. I've just arbitrarily called these buttons A, B, X and Y. And then there's another 3 buttons underneath, which is the menu, select and start buttons. And you can see there's a little perforated area. There's some pinouts where you can put a Raspberry Pi Pico from the back. So this will enable us to create a Bluetooth or Wi-Fi remote control for our robots. So this works with the power of MicroPython. So you can see, we can either have 2 direction control pads or just 1 direction control pad and a bunch of action buttons, which is what I've chosen to do. And optionally, you can solder on the OLED display screen, or you can leave that out. It's completely up to you if you want to use that or not. And it can be, of course, completely powered by a battery, whether it's one of these little, I love these batteries from Pimoroni. These are Gallium batteries. They are 3.7 LiPo, and they have that little connector on the end. I think that's a JST. Is it PH for power? I think it might be. And then you can also get these. These are quite popular with the BBC microbit. It's the same connector that's on those, and you can simply just put 2 AA batteries. I think that is in there. AA or AAA. I think that might be a AAA battery. Essentially, it's 3 volts. It's enough to power the robot. Might be on a bit of the weaker side with those ones. 3.7 is plenty. Between 3 and 5 volts, you're going to be working fine with your remote control and your robot for those. So let's have a look at these in a bit more detail so you can see the PCB in a bit more depth there. And if you wanted to recreate this yourself in KiCad or whichever package you prefer, whichever electronic design package that you prefer, you can do that. All the instructions on that previous video that we did back in August. So you can see on here we have the direction controls. We've got up, down, left and right. We have the 3 menu buttons, the user interface buttons, so menu, select and start. And when I came to look at this weekend, it was actually running the Pico Tamachibi code, because it's essentially the same pinout for those menu buttons, the OLED display and the Pico that's on there. And then on the right hand side we've got the action buttons, as I've called them. We have a battery connector. Just make note of which orientation when you solder a connector to that, that matches your battery. So on the one I've made, I soldered it on the front when I should have soldered it on the back, and because of that the voltage I kind of swap round, so the VCC is where the ground should be. So you don't want to be plugging that in, trust me. So we also have the 4 pins at the top there for the OLED display. There is actually writing underneath each one of those pins, very, very small, that actually says what each of them do. So I think it's ground, voltage, SCL and SDA for the OLED display. So I'll turn that down a little bit there. And of course we have the Pico mount to the back of the display. I'll show you that. I'll show you that now. Actually, let's just bring that on the screen. So here's one I made earlier. So this is the GamePad 2. You can see it's got the OLED display there, and on the back we have the Pico. You can see there it says the version 2 of this. You can see I've not really quite tidied up some of the flux on these. I'll probably need to get that off before it starts rusting, but very, very simple to put these together. You just need 11 of these tack switches. They're very, very cheap to buy. They actually just push in, but then just solder them on the back. The reason they push in is they have like little springy legs that hold them in place, so it's really easy to solder them. The only thing that's a little bit fiddly to solder, you solder in the Pico first, you push that in from the back, solder it on the front, and then put the OLED display on and then solder it. If you can get to the back, which you probably won't be able to, you might just have to solder it from the front just there. So it's a little bit fiddly to do that on that display there. But I've got it working, so if I can do it, anyone can do it. And on this one I've also got the connector. That should actually be on the back, and that's just for a battery. So very, very simple. It's a double-sided PCB, and you can of course buy these on the KesRobots.com store as well. So let's get over to what else this can do. So there you go, that's the simple version, and sure enough that one is actually running that Pico PCB code when I was testing that out. So the most important thing you probably want to know about this if you're going to be using this is what are the pinouts for this. So these are kind of hardwired to the Pico, and the great thing about this is you just solve that in place and everything else just works. So the buttons just work. So the up button is connected to GPIO pin 8, the down button is pin 9, left button is 2, right button is 3, and then A and B is 6 and 7 respectively, X and Y are 4 and 5, and then the menu select and start button are pins 10, 11 and 12, and then the OLED buttons, the OLED connections, the SDA, which is the data, that connects to the very first GPIO pin, pin 0, and the clock, which is SCL, connects to GPIO pin 1. So everything else has all the power connections that you would need. So if you plug in a battery, that'll power both the Pico and the OLED display, and everything else is kind of routed as you would expect. So what I would say as well, just to reiterate this, because I actually had this happen on one of my prototype boards. I'm not sure if I've actually got that still there somewhere. Probably not. I think actually it was the Pico PCBs. The display was getting really hot and nothing would display on it, and I was like, why is this not working? And when I checked the pinouts, the voltage and the ground on the OLED displays I'd bought were actually reversed. The clock and the data were the same, but the actual power and ground were different ways round. So definitely check when you're buying these online that they match the requirement of this board, which is ground voltage, SCL and SDA in that sequence. Software wise, so I've spent most of this afternoon, most of this weekend, and a lot of time on, was it Saturday night till about 2 in the morning, writing the MicroPython code for this project. So it's really easy to connect between two devices. Initially I had this working and it was so slow, it would take about 5 minutes to connect, and the reason for that was I was trying to scan for every single Bluetooth device out there and then seeing what services they had and whether that matched the service name that I was looking for. And you don't need to do that. You can basically just say, just connect to devices that are called, in this case, KesRobots, and it'll connect to that, and then it's just instantaneous. And it just, if it disconnects, it can reconnect. It's really, really seamless. So I'm really, really pleased with how this code works now. And it's really easy as well to draw text and whatever you want on this little OLED display. I've got a little program, we can have a look at that in a second on the demo. And of course this is completely customizable. It doesn't have to be for driving robots. You could have this as like a home automation thing and you just press a button and you know, it makes the blinds come down or whatever. It's entirely up to you. It's very, very easy to do this. So that's what Alex says there. I'm not the only one staying up too late coding this weekend. Yeah, I just wanted to get this one done. I knew I could do this. I'd previously done it on a different iteration. This is version 2 of the GamePad. I'd previously got this working. I think I'd showcased this when I was at the Rome Maker Fair. And I wanted to basically redo this and make the code a little bit better, with a bit better documentation. So, and of course we could also use Wi-Fi if we wanted to use something that wasn't Bluetooth. We could just connect to like an MQTT broker, for example, and you could send all those, you know, button down, button up to an MQTT server. That could then do what it wants with it, send it out to a fleet of robots if you wanted. So it's completely customizable and works with both the Raspberry Pi Pico and Pico 2. And what I would say is if you get to the with headers version, so this is a Raspberry Pi Pico 2W, WH. If you look on this, you can see that it has these little plastic, I don't know what we call them really, but the header pins have this little plastic thing on them, and that really helps. In fact, here's the with headers one of the original Pico. You can see this one has like a little struts that go across there. And these have been perfectly designed height-wise so that when you stick them in a PCB, just grab a blank BurgerBot one here, for example. So if I put this in here, if I push that all the way down, and then I'd soldered that in place, if I didn't have that little black riser, when I try and connect the USB cable in there, it wouldn't connect. You'll find that it's too close to the board. And that height is just enough that most USB cables, I don't know if I've got another spare one to hand, they will easily connect while that's soldered in place. So if you use the with header versions, you'll be out of trouble with that. So yeah, completely customizable. That's the main thing I want you to take from this. So assembling this could not be easier. Just take the 11 tack switches, momentary push switches, whatever you call them. These little things, I think they're 6mm by 6mm by 5mm. You can get the longer versions if you wish. You can get the soft touch versions if you wish. As long as they have the 6x6, they should fit nicely into these holes. And you simply just push them in place. It could not be easier. Flip the board round, solder them all up. Does take a little while, maybe an hour to solder the whole thing up, but very, very simple to do that. Like I said, assembly sequence-wise, you want to solder the Pico in place, so that Pico needs to be on the back of the board. So if I have this board here, for example, you want to get your Pico, put it onto the back of the board. So that's the front of the board that's got the text on it. It needs to go on the back of the board. That's because the pinouts are in that particular order. You can't just put them the other way around, it won't work. And then once you've got that Pico on board, then you can solder the LED screen, OLED screen on, and everything will be fine. And then it's just a matter of loading your code onto it and having some fun. So, like I've just said previously, I kind of got ahead of myself there. Pico WH, which is the Wi-Fi with headers, is best because of those little plastic standoffs that rise the USB cable to allow you to easily connect your cable to this. So if you can see there, the USB cable will go into the top there, and it's got plenty of space because of those risers to easily be connected. We'll do that on the other camera in a second so you can see. And you want to push the Pico in from the rear. On the rear of the board, there is also a little rectangle that shows you which orientation your Pico needs to be. So you can see on here, the USB needs to be at the very top. The top being, if that's the orientation, the GamePad like so. So you want it to be USB at the top. And there's a little rectangle on the silk screen that tells you that as well. And you can simply just push the OLED screen from the front and then just solder it. It's a little bit fiddly, but you can do it. Not a problem. Now powering the GamePad, I've connected incorrectly the GamePad power connector on this side here. Let's see if I can get that to focus there. And what I discovered when I looked at these cables which have that same kind of connector on it, if I was to connect that in there, look where the red is going to the bottom, and we need the red to go to the top because that's where the VCC is. If I was simply just to solder that on the back, I could solder it in that orientation so that they go on correctly. I mean, I could even probably just turn that round and that would work. Just something to be aware of. And it's safe for between 3.3 volts, 5 volts, possibly up to 6. Depends what your Pico's voltage regulator can drop that down to, but you don't want to be burning that out if you can help it. So these LiPo batteries are typically 3.7 volts, 4.2 if they're fully charged, down to about 3.2 if they're like the bottom end of the charge, and that's within that range. That's it's fine for our Pico to use. So the OLED, as I've said, definitely check that the OLED pins prior to purchase. Some have the voltage ground the wrong way round. I've fallen afoul of that, and when you purchase them, I think they usually give you a bit of a screenshot. Depending where you buy them from, if you buy them from a reputable place, it'll probably be the correct orientation as it is on the site. If it's somewhere that's very, very cheap, they might just use a stock image, and it's just a roll of the dice whether you get the ones that are correct or not. So definitely just check for that when you're purchasing those OLED displays. And the OLED displays are called SSD 1306 displays. I think these are 128 by 64 pixel. On the website, I actually have a full write-up and bill of materials, so you can follow along on there as well. I'll show you that in a second. And if you like what I do and you want me to make more of these types of videos, please give this video a like. Drop me a comment what your current project is that you're working on and how that could be better if you had a custom PCB. I'd be very interested to know that. And if you haven't subscribed already, please subscribe. It means an awful lot to me. I love seeing those numbers go up every single day, and I'd love to get to 100,000 subscribers. That would be an amazing thing in a couple of years' time, but more than likely. I do go live every single Sunday at 7 o'clock GMT, so if you want to follow along and have a chat after the main show, then you can definitely do that if you hang around. And yes, follow along. Okay, I'm just going to move that on that screen there so I can see what's going on. I wanted to as well just celebrate Minnie's birthday today. My little doggy is 6 years old today. That's Minnie on the right hand side there. She's a little Jack Chi, or Jackawauwa as we call her. So this is a Jack Russell Chihuahua cross, as is Archie, who's at the bottom left there with his little hat on. So yes, both of these are our little doggies. They like each other very, very much, but Minnie's my dog. She likes to sit on my lap in an evening. Even if I've got my laptop on my leg, she'll be like at the bottom of my legs. So she'll be helping me code along there. So happy birthday, Minnie. Right, so let's have a look at the main code that I've been writing for this. I'm just going to give you a quick overview and then we'll get into like a demo and show you how this actually works. So the code library, GamdPAD.Py, actually has a number of different classes within it. So there is a GamePad class, there's a GamePad server class. I should have probably called that something else. I'll explain why in a minute. And then there's the button class, which is just a very simple kind of handy utility for checking buttons are pressed or not. Very, very, very simple to set up. So if you want to use the GamePad PCB with a Raspberry Pi Pico and you want to use MicroPython, then you can simply just copy this GamedPAD.Py to the Pico, and similarly you can copy this to a robot that you want to control with the remote control. It's the same library. You just use either the GamePad or the GamePad server, depending on what the use case is that you're looking for. Now, I've said on there, optionally, you can copy the SSD 1306, which is the little display driver. I think you actually have to copy that. It's optional whether you solder that onto the board or not. You don't have to do that. I think it's just a bit easier to use a control if you have that. But you don't have to use that. But you do have to copy the code because it'll just say that it can't find it. So there's that. Okay, so we'll have a quick tutorial on Bluetooth connections using MicroPython, because it isn't the simplest thing to get your head around, I would say. So you typically have a peripheral device and a central device, a client and a server. You could look at that. So the reason I said I named that previous class wrong is the client is actually sat on the right hand side there, and in the server thing we have the little gamepad. So from a client server perspective, I've kind of got that back to front. Ignore that, it just works. So we have essentially these work in lockstep. So a server will advertise its services. So it typically say, I've got a service and these services have characteristics. So a service might be like a temperature sensor, and a characteristic might be humidity, temperature, air pressure, and so on. And you can have as many of these characteristics and services as you like, but they are kind of hierarchical. Now we simply just want to pick a pair of a service and a characteristic, because we simply just want to push buttons and have that be sent over Bluetooth. We could optionally look at in the future as well pushing graphic stuff from the robot to the remote control. So for example, these robots I'm working with have a rangefinder on the front, and we could visualize that distance on our remote control by sending back from the robot to the remote control the distance. So we could do that over Bluetooth as well, because it does work in both directions if we want that to. So advertising out those services and characteristics is something that we need to be able to do. And on the client side, we need to be able to discover and scan for services and characteristics. Once we have found something that we're interested in, we can then make a connection. So once we've found the service that we're interested in of a particular device, we can say make a connection to that. And that's handled by the Bluetooth library, which is part of MicroPython now. Once we've got that connection, we can then do some data transfer. We can send and receive data, simply doing read and write to the Bluetooth connection. It's very, very straightforward to do that. And something that will happen throughout the life cycle of your code is that you'll get a disconnection, whether that's purposely done or if the battery runs out, or the robot goes way beyond the Bluetooth strength, the signal strength, or you go out the room or whatever it is, you'll get disconnections happening. So we need to be able to handle that gracefully in our code. So they're the 4 stages: advertising, connection, data transfer, and disconnection. And that's on the server side. And on the client side, discovery and scanning, connection, data transfer, and disconnection. So if we have a library that can handle both of those parts, we've got everything that we need to build some robots that we can remotely control. Now the first thing is when you write programs in MicroPython, typically you're writing synchronous code. You're writing code that goes in a very simple, straightforward sequence, top to bottom. You might execute some functions, but everything's done kind of in a linear way. And that can actually cause problems. So say we had a piece of code that turns an LED on and off to indicate like a connection status. When we're doing that piece of code, nothing else can be happening in the rest of our code. So what happens if our robot is flashing a light and it's also like trundling towards a cliff edge, and there's another sensor that could detect the edge, but we're not currently looking at that. So that would be catastrophic. So when it comes to writing robot code and code that we want to work asynchronously, synchronous programming really won't work. It's called blocking code because it's being blocked from doing other things because it can only do one thing at once. So it's great for simplicity and predictability. We know exactly what's going to happen in what order with synchronous code. It's sequential in how we write it and how it's read, and tasks are completed before moving on to the next one. So that's a typical kind of old-fashioned synchronous programming. Asynchronous programming is a whole new ball game. So it's non-blocking, so we can do things at the same time. Essentially, we could have a light beam flashing on and off. We could have another piece of code that's scanning for Bluetooth devices, another one that's waiting for that to find something, and then it can take over and say, let me handle that. I'll now send the push buttons, for example. So we don't have to wait for one task to complete before moving to the next one, and that can really improve the efficiency of our code and our resources. This can be also known as event-driven execution. So ideally we're waiting for events to happen, we can then capture them, and then we can act on them right away. And we do need to be aware of the responsiveness of our code. So when an event happens, we can't have like a really big chunk of code doing lots of complicated things. It's typically best to have lots of separate tasks and allow time for those tasks to happen by putting in your code essentially a sleep statement, but it's an asynchronous sleep, which means I don't need to do anything for a while, hand the control back over to another task, and the task scheduler will figure that out. So this is called cooperative multitasking. It's not like preemptive multitasking that we have on all modern computers, but back in the day, this is exactly how, say, Windows 3.1 worked or Macintosh System 7 worked, that they all use this similar kind of cooperative multitasking. So we need to be able to use that in our code. So synchronous code is great for very simple things, and then asynchronous is what we need to use for Bluetooth low energy edition code. So how do we actually use this then? So there is an Asyncio library that we'll need to import into our code, and then we need to have the word async in front of our function definitions, and that tells MicroPython that this is a special type of function that can work it can work at the same time as other functions that are also asynchronous. And when we want to wait for an asynchronous function to return some code, we can use the await keyword, and that simply means I'll just sit on the bench while I wait for this function to finish working, and you can go and do something else, Mr. CPU, while this is happening. So it's really, really cool. They call these coroutines, and you have to use that await on any function that has the async. If you don't have that, it will grab the data immediately, but it's blocking. It doesn't allow any other coroutines to work. So what else we have? We have async.run. So once we have all our tasks defined with our async definitions, we typically want to create a task using the Asyncio library. We can have quite a few tasks. We'll have a look at those in a minute. And they're simply going to be pretty much what we've seen on that first slide where we had the advertising and scanning and discovery, the connection, the disconnections, and then the actual main code that we want to do something like pushing buttons and sending them over Bluetooth, or receiving button presses and then making our robot move. So we need some kind of event loop for that, and that's what the Asyncio run function does. So we'll create like a main function, we'll make it an async main function, and then we'll say asyncio.run and then main, for example. We'll have a look at the code. It's a lot easier to see it than to kind of explain it. But essentially, that's what we want to do. We want to run a sequence of tasks in a special event loop, which is using this Asyncio library. And remember, non-blocking means that we want to write all our code in such a way that we don't block other pieces of code from running. So it's really cool for doing things that are really quick to return, like checking a GPIO. That's a really quick operation in MicroPython, as is like turning on an LED, because you're simply just flicking a bit. And then if you want to set a status to say that that LED is now on, you can even store that in a variable too. So very, very simple to do that. You can have nested coroutines. We just need to use that await to say that it's awaiting for another coroutine to finish. And of course we also need to do exception handling, but remember, exceptions that may affect other tasks that are running in the event loop, so we need to be careful how we do that too. We also need to classify our data, so we have these BLE services, we have BLE characteristics. Characteristics are part of a service, and a service is something, as it says, an example is heart rate, and a characteristic of that might be the heart rate measurement. I think that's a poor example, actually. It's probably easier to sort of say that you have an environmental sensor service, and then you've got individual characteristics such as temperature, humidity, pressure, and so on, air quality. So once we've classified our data, we can have that as part of a service. We can have multiple services, multiple characteristics, and it's all that in that kind of hierarchy. And the way that these are identified, so if I was to create, for example, a set of scales, weighing scales, I would actually have to find out what is the Bluetooth special interest group code. They have a unique, universally unique identifier for each different type of class, each type of characteristic and each type of service. So we need to find one such as like a button characteristic, a remote control service, and if we use them, other devices could also play along nicely with them too. And I have actually got a utility that I use on the Mac. I'll show you that when we do the demo, that you can actually detect our remote control, and you can see the services and you can see the push buttons happening in real time. It's really satisfying to know that that's code I've written and it's working live, as it were. So how do we actually send the data? We have these individual data points that we collect, such as button presses, temperature sensors. We then encode that, because typically we might have a string of text or a button, which might be binary. We need to encode that in a form that Bluetooth understands, and then when we send that, we can send it in that format, and then when we receive it, we need to unencode it. We need to decode it back into that form. So there's very simple encode and decode functions that we can use for that as well. You can see there are actually some of the service unique IDs and characteristics as well. So let's get to it, shall we? So I'm just going to flick over to me for a second just while I get my screen sorted, and I'll show you it working first, and then we'll get into the code of how this actually works. Let me just jump over to this camera view here, and what I'm going to do, I'm just going to plug this directly into just the power, and you'll see on this camera here it says connected. And if I now press the forward button, this little robot here is going to fly along the if I do backwards, if I do left, it's pulling slightly because of this cable. If I do like left or do right seems to be a bit more vigorous there. So this is a little burger bot. I've just got this powered by a US key cable, and this is just powered by a regular Raspberry Pi micro SD connection. So you can see there, we've got a little task that's just flashing the LED. If I'm to disconnect the robot, watch that flashing LED, because that flashing LED is actually also indicating the connection status. So it's flashing quickly now. That indicates that it's not connected by Bluetooth. If I now power that back in, my little robot's wheel's going to fall off. It always does, but that's actually handy because there's a little button in there I need to press anyway, so that's why that's just fallen off there. And you can see now that it's connected, that's how quick it connects. It's now flashing once per second. And in fact, if we flick over there, you can see the little OLED display has the word connected. If I disconnect that, you'll see that it'll detect that it's disconnected. If I power that back in, hopefully you can see this when it comes back on. Let me just power that up, press the power button, and you'll see that it will say connected very shortly. There we go, it's connected again. So it's very, very simple and very, very quick to connect. And when I press these buttons, that robot is actually going to move forwards and backwards. And you can also see on the screen, it's actually telling me what buttons I'm pressing. So left down, right up. So there's 2 events for each button press. There's an up and a down. We also have the menu, select, start. We have A and B, which I've also got connected to the pen up and pen down on this, but I've just broken that before the show. There's a little cable that should be connected that's it's just ripped off, so I'd need to solder that back up to get that working again. And we've also got X and Y as well. So this little OLED display is showing me all kinds of information on there. You can see, if I do that again, if I press forwards, backwards, you'll see that it says down, up and down, down. What I mean there, up, down, left and right. And there's 2 button states for each button, which is start is down, start is up. And it'll just show you the last state of each button. So that's how we get that working on there. And I've loaded some code onto this, such that when I provide power, I could actually have this running off a little LiPo battery that just sits inside there, but I didn't have time to disconnect all this and put the battery in and make sure it's all powered up and everything. So these little batteries are absolutely great. You can also just check that they've got power using the little LiPo Amigo Pro from Pimoroni. They've got these nice little chargers, and you can also turn that on and off, and you can just provide via USB-C a connection there to power it. And if you wanted to, you could have that go into another device. So you can have power either through USB or through the battery. But I can see that that's actually powered up, and this is a charger as well, so if I plug that in, it'll charge up that little battery just fine for me. So this is a BurgerBot. I also designed this other BurgerBot. This is a kind of work in progress at the moment, but this will work in exactly the same way. It might have slightly different pinouts. The reason that these horrible wires here is when I designed this PCB, I didn't measure this correctly, and I was intending for that to just sit on some header pins there, and I didn't get that quite right. I did get, however, the Pico pins absolutely perfect, and there's some header pins that you can see there, which is for the motors, and also for the rangefinder. That simply just slots into place just there, and we've got a very simple robot. I use these little N20 motors, and they just connect to the motor B and motor A, and essentially that's all that's happening inside this this 3D printed version. However, this one has a couple of extra little headers on there, so it has, I can just find the little circuit that I put on here somewhere before the show started. So Pimoroni do these really cute little packs. So this one is a LiPo, shim, sorry. This one is a LiPo shim, so you can put your little battery in there, like so. You can power it on. If you pick a battery that's actually got some power in it, let's try that one because we know that one works. I've expected a little LED light one. Maybe it's not got quite enough charge to make that work, but essentially that's all that's in there. There's a Raspberry Pi Pico that's got the LiPo shim on it. I think it works like that, and it provides power to the Pico, and you can actually stack other motor shims on there as well, which is what's going on in there. So let's have a look at this. We'll plug this into our computer and we'll have a see what this actually does. So we'll put that there, and let's get over to our code. Right, let's have a see what we've got going on here. I've got a little script that I can look at. Make sure I'm doing this in the right order. Right, so let's have a look at test buttons. So if I go over to test buttons, so this is a piece of code that I've written just to test out that the GamePad buttons actually work, and we can also have a look at some of the other interesting things on here. So I've got this Asyncio library. If you run MicroPython and this doesn't work, it says it hasn't got the Asyncio library, you need to make sure that you're on the latest version of MicroPython. So I'm using the kind of standard MicroPython. This one is actually a bit of an older version. I could actually flash this with the 1.24.1, which I think is the latest version as of the recording of this, but this works fine, I think. So that's connected to the GamePad. So we've got the Asyncio. A GamePad is a little file that we'll have a look at in a second, but essentially the GamePad is there. I need to copy that to my Pico for our program to actually work. So if I do upload to, it's the same size because that's the actual version that we're using there. I've also got this boot.py. We'll have a look at that in a second. Main.py is the code that runs after boot.py. So you don't have to have a boot.py, you don't have to have a main.py, but when you apply power to your Pico, if you want the code to run automatically, you just need to name it main.py. I think if you used to CircuitPython, they have code.py, which does the same thing, but it's main.py on the Raspberry Pi Pico standard MicroPython. Okay. So let's have a look what we're going to be looking at next. So I've got then, after GamePad, I've got two functions and I have a little main loop there. So the first one is test GamePad. So it says GamePad equals GamePad. So we're going to use that GamePad class that's in the GamePad.py file. We're going to say starting GamePad, and then we're going to await for the asynchronous I/O to gather its tasks together. So we can provide a whole bunch of different tasks, and we can then make it start once it's got those tasks. So I'm saying gather GamePad.main, which is inside the GamePad file. We'll have a look at that in a minute. And also monitor start button, which is this piece just below. So they're the two tasks that we want to work at the same time. We've got this next one, which is def monitor start button, and we're passing in the GamePad library there as well. So this is going to it's going to test every one of the buttons. It'll print it out to the screen, and if we press the start button there, it'll then exit the code. It'll say that the code is finished. And this little loop down here says if name equals main, which means if you run this script and it gets to this point and it hasn't got a main program, then you can basically just intercept the code running here, and it'll say async.io.run test GamePad, which is this this task that gathered all the tasks together, and that's going to run the main event loop for our async.io. So let's actually run that, and I'm going to say run, and if I go to the overhead there, we can probably look at the code at the same time as I press buttons. So you can see it says GamePad on there, and if I press the up button and then I release it, button up, button down, left, up and down. So when I press the button down, that's one event. We may want to catch that as a specific event, so we want to know when we let go. And down, we've also got the menu select. We've got A, B, we have Y and X. And you can also see on the screen there, as I press this, we're actually getting the name of the button being written to the screen as well. And if I press the start button, it says exited, but it carries on because we've actually not exited the loop there. So what we'd actually have to do is, once we've captured that, we'd have to say asyncio tasks cancel, and cancel all the tasks that are in there. Otherwise it'll just carry on doing that forever. So that's showing that the actual buttons work. And interestingly there, we have two events per button press, one where we press button down and one where we release the button up. And we might want to use that to make our robot a bit more fluid in how it moves. So what I did previous to this, this type of code, if I press the forward button, if I pressed and held it, there'd be another loop on the robot continually checking to see if the forward button was being pressed, and if it was, it would make the robot move kind of forward for 1 unit, and that might be like half a second, and then it would stop. So if you held it down, you'd see the robot sort of jitter forward and jitter backwards because it didn't really handle the release of the button very well. So we could have our code that makes the robot start going forward once you press the down button, and when you release it, that's another event that it could capture, and that makes the robot stop, for example. So we just need to think about how do we want to actually use these button presses in our code. So that's the first one. Let me see what else we have on here. So let's go for the OLED next. So I'm going to load up the test OLED. And this is a very, very simple piece of code. Let's have a look at this. So from machine import I2C. Then we're saying from SSD 1306. that's a little library that I wrote quite a number of years ago now for MicroPython, which does all the kind of backwards and forwards bit bashing to make this display work. We need to provide an ID number, which is the ID of, is it bus 0, bus 1 for I2C. You get 2 buses on every every Raspberry Pi Pico. We're going to use the 0 because 0 is the collections of pin pairs. So you have SDA, which is the data, and SCL, which is the clock. And data is always going to be 0 and 1, or it could be another pair, though. I think 3 and 4 can be used. There's a whole bunch of pairs, and I think it's like every other pairing of pins on there. You check on pinouts.xyz, you'll get that kind of information. Once we've got that, we can then create an I2C object. So we say I2C in lowercase is equal to our I2C class, which is coming from machine. And we need to pass in the SDA, so SDA equals SDA, SCL equals SCL, and the ID equals the ID. Once we've got that kind of connection to our device, and we need to then use the SSD 1306 driver for our display. I'm just going to call that OLED because that's, call it display, whatever you like. And we pass in the number of pixels wide. So what's the width, the number of pixels for the height, and then we pass in the I2C object that we've just created there. And then it's simply a matter of then saying OLED.text. We can pass in a string of text. We then say where on the screen we want to start that text. So 20 and 30, and the coordinates of a screen start at the top left, so that's 0, 0. So the more that we increase the width, the further to the right it will be, and the more the height, it'll further down the page, if you like. And we also need to do an OLED.show. Now OLED.show is where it takes all that information from its frame buffer and actually makes it appear on the screen. And there is kind of a time cost to that. So typically, if you're doing lots of drawing things on your screen, you'll do all those separately and then you'll do a show after that. If you did that after every operation, you would see a bit of flickering and it would actually take quite a bit longer of time. So that's just something to bear in mind. So what I will do, I'll just hold this up to our little display again. Oops, that's not the one I wanted. There we go. And I'm going to run that code that we've just created there, which should say GamePad 2.0. So that's all that code does. It picks a font, which is the default font. I think you can change different bitmap fonts on here. There isn't like a crazy amount of these, but there's more than one. You can even design your own fonts as well, which I did. I created a Johnny 5 font, as I called it, because it was 5 pixels by 5 pixels. And there's also a proportional size as well, so not every single character is the same size, which they are on these ones. These are fixed width ones. So that's how very easy it is to use the OLED display from within the GamePad. So I built that into the GamePad library. Let's have a look at that. Let's have a look at GamePad, the test GamePad code next. So this is the code that I've written as a kind of test program to show that the GamePad works properly. It's what I was using to drive that robot a minute ago. So I'm also using my BurgerBot code. This is some code that I've kind of customized for this particular 3D printed robot. Like I said, it'll work very slightly differently on this circuit board version of the BurgerBot, just because the pins are different, but we can change that. But all you need to know is that GamePad server is going to be the thing that we put onto our robot, and GamePad is the one that we'll put onto our remote control. So this is the code that's actually running on the robot itself. So you can see bot equals BurgerBot. So whatever BurgerBot does, bot can now use all that. We can set the speed of our BurgerBot. What I was finding was if I had a slower speed, it might not actually be enough power to make the robot move forward. So when you can hear that sort of whining sound, that's probably what's going on there. I've got a couple of tasks then. So we've set up an async task. One is monitor the GamePad. So while true, and as it says there, this is really ugly code. There are much better ways of doing this, but this does just work, so don't feel bad if you do a similar kind of thing, which is just an if with loads of if-else's all the way to the very bottom. So we're saying GamePad is up, so that's checking is up button. So if we press the button for up, is down pressed, is left pressed, is right pressed, and they're also doing so if we press the the up button on our pad there, we want our robot to move forward. So that bot.forward is the BurgerBot code, which will make the correct motors work in the correct sequence to move the robot forward. Today's show isn't really about how the BurgerBot itself works. We've covered that on a previous show. If you want to find that out, go to kesrobots.com/BurgerBot and you'll find all the coding videos for that. So we've got some other checks there. So if A is pressed, make the pen go up. If B is pressed, make the pen go down. And then just display text to show that each of the buttons is being pressed, and we can see that on our screen. If nothing is being pressed, then we want the robot to actually stop, because if we're not pressing any buttons, it shouldn't be sort of carrying on going. Pass simply just means don't do anything. I had that before. I had the bot.stop included in there. And then we've got this little await Asyncio sleep. So it says there, avoid tight looping. If you don't have that, your code will continually execute this while true, and it doesn't really give a chance for any of the other tasks that might be waiting to have their turn to actually go. And this is like a tenth of a second. It's more than enough time to be waiting for a keystroke. Humans don't work that quickly, so that's fine. Here's our main loop, so our syncdef main. So this is the main code for our GamePad server, which is running on our robot. So GamePad equals GamePad server. We create a couple of background tasks. So I like to have a blinky task. So the blink task will make the LED on our built-in LED on our Pico flash on and flash off. And we can even show the connection status by the speed of the flashing. So it'll flash very quickly if it's not connected, and it'll flash once per second once it has made that Bluetooth connection. So our little blink task, which is inside the GamePad library, we'll have a look at that in a minute. And we've also got the monitor, which we created just up there, which is that horrible piece of code. And we just pass in the GamePad that we created there as well, so it's got access to all those variables that are within it. We then want to append those tasks to our tasks queue, which is inside the GamePad library. So GamePad.task append the monitor and blink, and then we do await GamePad.main. And inside our GamePad, which we'll have a look at in a minute, there is a main function, and that's then gathers the task together and starts the event loop. And we can also say that while true, Asyncio run main. If we have a situation where we interrupt this on our keyboard within the console, we can then say exit in, and we can exit from that code running. So that's our test GamePad. That runs on the actual robot itself. If we want to look at the code that runs on our GamePad proper, it's the code that we've just looked at, which is this starting GamePad. Let me just make sure that is actually correct. Test GamePad and test buttons. Yes, they're the two that I've created for this particular show. I also said I would look at the boot.py as well, just for reference. So this simply just says check to see if pin 12 is the start button on the GamePad. If that's been held down when power is put in, just exit out, because sometimes if you've got a main.py, you try and connect to Thonny, you click that stop button, it doesn't always honour the stop, particularly if there's these coroutines running in the background. So this is a way of making sure if you want to drop out to the REPL like this, you can do in Thonny just by having this little boot.py, which runs when you very first put power on. It then hands control over to the main.py, which is there. If you wanted to see some of the other pieces we've got in here, so we've got a motor.py. This one simply just models a motor. You typically have a motor driver such as this one here. This one is the MX1608, I think it is. Of course, you have the L298N, and there is also MX8833 and that kind of variation. They're like the really, really small ones. They all work in a very similar kind of way. You typically have 2 pins for each motor, and you'll have input pins and you've got output pins. The input pins are the ones that control the motor's direction and speed. The output pins actually drive the motor. And you'll typically also need some external power to power the motor, because the Pico hasn't got enough juice to do that on its own. And that's what we use these for. So this initialization piece will take in pin 1 and pin 2, the input pins. It'll identify one as being an input pin and one being a pulse width modulation pin. So pin 1 will do the direction, so it'll be kind of positive or negative to make the motor go spin forwards or backwards. And the second pin will define the speed that the motor is going at. We also, because we're using pulse width modulation, need to set a frequency. We typically set 1000 for that. The speed then we can check to see is a floating point number between -1 and 1. So it could be 0.5, for example, for half forward speed, or minus 0.5 for half speed in the other direction. We've got a bit of error checking there just to make sure that if it's less than 0, we can make that go in the reverse direction. Otherwise, it's going in the positive direction. And we also want to set the speed by taking the absolute value of that number and times it by 65,535, which is 2 bytes. And that will define the pulse width modulation for that particular motor. We've got brake, which is we set both of the pins high. That should stop the motor. It should make it sort of rigid and hold it in place. Otherwise, we can drop both of the inputs to be low, and that'll just make there's no power going to the motor at all, and it'll just spin to a stop. So we can use brake or coast. And I think I've also called these in other bits of the code disable and stop. So I've basically made both of those coast as well. Right, so have a look at the GamePad code. This is where all the major stuff happens. It's quite a beast of code, but I have written up on kevsrobots.com all the different functions for this. There's if you go to GitHub as well, Kevin McAleer /GamePad, you'll find a functional reference for all the things that are in here too. So we are using the IOBL, which is the Asynchronous I/O library for Bluetooth Low Energy edition. We've got Asyncio, which is the Asynchronous code library. We're using some constants in MicroPython, so we're importing that. We're using Bluetooth, so we're importing that too. We're importing the ticks MS and ticks difference. So ticks is a way of seeing how many units of time have happened since you put power into your MicroPython device. And that number can essentially wrap round like a speedometer. So you might have a number that's going like 5, 6, 7, and it gets to 99999, and then it'll wrap round to 000 again. If you're trying to compare two time pieces of time using the ticks MS, you've stored them in some kind of variable. If you try and compare like a really, really high number that's then wrapped round to a low number, you're going to get some kind of weird thing happen. So if you use ticks diff, you don't get that happening. So that's something just to bear in mind there. The SSD 1306 is the driver library, and we're using the I2C version of that, which just uses the SDA pin and the SCL pin. And we're also bringing in the I2C library from Machine as well. I've defined a bunch of pinouts. This is actually from the PCB design itself, where we've hardwired each of those pins. There's a traceable route that goes back to the Pico that's been soldered in place. So that's the pinouts for each of those. We can simply just do GamePad.A_button to find that if you can't remember what those are. I can't remember what they are, and I made the thing. But there they all are as constants. That's why they're all in uppercase. We've got the button class. I think you could save that out to a separate file if you wanted to, but I've just included it because we make such heavy use of it in the GamePad. So we've got a debounce, which is like when you press the button, how long before you accept that you've let go of that button, for example, so you don't get these weird electrical things where it's kind of half in and half out, and you get kind of false positives that the button's been pressed. So by debouncing it in software, you don't have that problem. And we have the is pressed, and that's where this time ticks MS comes in, and the ticks difference comes in because of that wraparound that we talked about with the speedometer. It compares the current time to the last time it was pressed, and if it's greater than the debounce, then we can say last press was current time, and return true that it has been pressed. Otherwise, it's not been pressed. And we can also check to see if the state has changed, and there's lots of, if it was pressed and it wasn't pressed previously, then say self-press was true. Return true and false, and so on. So you get like a little tuple of what the states of the button are. Then we've got the GamePad itself. So we set up a dictionary of buttons, so button names and pin buttons on there as well. So that's an actual button class from the class that we created before up there. One of them for each of the buttons. We've got the onboard LED as well, so we can access that through the self.led. We've got two for is it connected or is it not connected, and when it is connected, what are all the connection details? So what's my MAC address, for example, that kind of stuff. We then need to set some universally unique IDs for what the service is that you're going to be using and what the characteristic of that service is. So we've got a generic UUID, which is that number there, and we've got a button one to basically be able to send button presses over Bluetooth, and that's that number there. We then need to set up our device, so device info equals IOBLE service. So we're going to set up that with the generic UUID, and then we're going to set up the button characteristic again with the IOBLE characteristic function. We pass in the device info, we pass in the unique ID for the button, and we set this read and notify to be true as well. And that's how when you're waiting for an event to happen, you can either read that event and poll it, or you can be notified that that happens. So Bluetooth can handle that as well. We then register that device, and that registers it in our little Bluetooth stack. We just need to have that happen. And then we then set up our OLED. So all that thing we did in the OLED test before, it's exactly the same code there, but we've said self to OLED, so we can refer to that in the rest of any part of our code later on. We can just do OLED.text and OLED.show to show that. Then we just print to the console GamePad initialized. So the monitor buttons is kind of a fancier version of what we had in that test code before. So this is going to continuously check the states of the buttons, hence this while true. And then for name button in self button items, which is the name of that list that we've got there, we want to have button up and button down state changes for each of those buttons. The connected text, which we use to show on the screen, is just we want to have the state of our Bluetooth connection display on our screen, and we need to have some text for that. So rather than just writing connected or disconnected depending on whatever the state is, I've just got it done at the top there. So if the button is down, if we press the button in, we want to print to the console button has been pressed down, so we can see that down here. But if we're using this and we're not connected to a computer, we'll not see that. So we can actually make it display on the OLED display, which is cool. So fill 0 just makes the screen kind of cleared. Writing the text, so whatever the button is down, we're using an F string for that, so that bracket's name will be whatever the variable is for this particular button. We're in a loop, so that'll change for each of the buttons, and then we're making that appear at 0, 0 on our screen. We're then saying whatever the connected text is, at the bottom of the screen as well, so that if it's connected or disconnected, that'll be continually updated. And then we do the OLED.show to update the frame buffer. If we're connected, if we've actually got a Bluetooth connection, then let's write that to the that characteristic, and we're going to encode it as well using the encode function. We don't need to specify what type of encoding that is. It has a default, which I think is UTF-8. And then we can also notify self.connection as well, which is just kind of doing the same thing, but a different method. Otherwise, if the button isn't down, then the button is up, so we can say that the button has been released. We can put that on our little OLED display, and we can also write that to our Bluetooth if we have a connection. And then, like I said before, we need to have a little bit of breathing room for any other cooperative tasks that are running at the same time, so await sync IO 10 milliseconds for that. Now, on the GamePad, we've got a peripheral task, so we need to be able to advertise out that we're a GamePad. If anybody wants to know and connect to us, here's all our details. So this sync await IOBLE advertise, we wait for this many, I think, milliseconds. We say this is the name of our device, so Kev's Robots, and the services is this generic UID that we've said. And we have all that as self.connection. So that's where that connection information will be stored. Once we have that connection, we can say clear the screen or fill 0, use these interchangeably. We can then write connected on the screen. We can then show that, and we can also say to the console connected from whatever device. We actually get a little MAC address of the device. And then we have the connected is true, so that's now flagged up. And we can use that in other parts of our code as well. We can then await the disconnection of our device. It'll happen at some point in our device's life cycle, and await will sit there until that happens. Once it's happened, the rest of this code will then run. So it'll clear the screen, say disconnected, print disconnected. We've then got a little blinky task. So this one just prints to the console that the task has started, and then it'll just carry on forever while true. Self LED toggle. So if it's on, it'll be off. The interval, we've just set that If it's connected, it's every second, otherwise it's 4 times a second, and we will await async sleep. So we're just going to wait whatever the blink interval is, because that can change. If we're connected or not, it'll sleep for that amount of time, and that'll essentially have the effect of making it flash very quickly or flash once per second if we're connected or not. And then finally on this block of code we have the main code. So here are tasks. So tasks is a little list, and we have to create some tasks in here. So we're creating the peripheral task, the blink task, and the monitor buttons task. Once we have those, we can then say Asyncio gather those tasks. So star tasks means unpack that list. So it's essentially as if we created gather and then Asyncio create task, peripheral task, and so on. So that's how we add all those tasks to our little queue. We need to run those tasks in a second. So we've got this def begin, print gamepad starting Asyncio dot run self main. So that will actually make that event loop start. And that is the gamepad code in its entirety. So 160 odd lines, and it's probably not even that because some of that was the button stuff above. Then we have the gamepad server. So this is the code that runs on the robot. So instead of having to advertise, this one will need to scan for devices potentially. So in our init for this, the device name is Kev's robot. So that's going to be paired with whatever the remote is. So we need those two to be the same. The device name is going to be equal to what we've just set or passed in there. The LED is going to be the built-in LED. Connected is false, connection is none. The command that we've received is none. And the tasks are going to start out as nothing. We're going to set the same pair. So this is how we kind of pair our Bluetooth device immediately and automatically. We have the same service and characteristic IDs in there. We've also got this BLE appearance generic remote control. I'm not sure we actually use that, to be honest, so we could probably take that code out. We then register that service with the remote ID, which is the same one as we've used for that generic one above, and the button characteristic is also registered as well, and then we register those services with that services self remote service. We then got our peripheral task. So this is going to loop round forever. We say device equals await self find remote. So find remote is some code below. That's going to be the thing that does the finding of our remote connection, and once we have that connection we can then drop down into this other code. So if there's something happens weird in there and we pass through and it's not a device, we can say remote not found, retrying, continue. That will essentially start the loop again and try and find the remote. This try except block will then say connecting to the device, because we've got the good connection. Connection equals await device.connect. That's the actual connection happening over Bluetooth. Once that happens, connected can become equal to true. We can then say that we've got that connection, and then with that connection we can say await for the disconnection to happen and then print disconnected from remote. Otherwise an error has happened, and finally we can say self-connected is false, async sleep for 2 seconds to avoid aggressive reconnection retries. The blink task is exactly the same as we have above. I think it's just written in a slightly easier to read method there, so that simply just toggles it on and off whether we're connected or not. And then we've got the read commands. This is the thing that's going to read those commands over Bluetooth from our remote control. So if we have been connected, and if the service and characteristics, if not service or not characteristics, this is a way of speeding up that connection. If we've run around this before, we can use what we already have. So if we haven't got this, service just needs to wait for that service connection to complete, and the characteristic is the same as well. That'll happen pretty much immediately because we've specified them above. While we are connected, we can say value equals await characteristic.read. That's the piece of line. That's the line of code that grabs the code from our remote device to this device, and then we can then say if we've actually got a value through, self command equals value.decode UTF-8 strip and lower. So this is stripping off any spaces, white space before or after, and making sure it's all in lowercase, just to make our code easier to use later on. And then we have an exception just in case anything happened there. We can just disconnect. That's the easiest thing to do if we have any problem. Just disconnect and try again. Then we've got a bunch of properties. So we might want to look at our gamepad and say, has the up command been sent? So if self command is up down, which is that the up button has been pressed down, we can then say that is up is true. So it'll return true for that, because that's a little condition there. The decorator at the top means that we don't have to have brackets after is up. We can just look at it as if it's a variable. And we've got one of those for each of the different button presses that can happen. And then the fine remote code, this is the piece of code that scans for the Bluetooth device. So we've got this IOBO scan, so 5 seconds. We've got intervals, windows, active true as scanner. And then we can say for result in scanner, if the result name is the device name that we're looking for, Kev's Robots, then say you found the device, return that device, and then that can be connected to in our other code further up. And again, we've also got a if the device isn't found, we've got no wait there, just to give all the code routines some time to run. And then we've got our loop, our main loop. So starting tasks, we've got 2 tasks, we've got a read commands and a peripheral task. So we append those to our tasks. We then gather those tasks, and then we have the if there's an exception for task in self-task, cancel the task, and that will stop all the tasks from running. Otherwise, if you look down in the console, you'll see that other things are happening, and it's as if something's happening in the background, because it actually is. That's all the code that we need to make our Bluetooth work. So let's have a look at that again. So I'm just going to go back to our test gamepad. I'm going to run this code, and we're going to connect to our robot. So I just need to provide our robot with some power. So let's go over here. I'm just going to connect this in, this time through there. I can see that there's a light that's in there. I'll put our wheel back on there. Just trying to get that so that it doesn't tangle up too badly. And we have over here our code ready to run. So if I click on run on this code here, this is the test gamepad, test buttons I need to be on, sorry. Let's run this code. So you can see there it says starting button not pressed, continuing, gamepad initialized, starting gamepad, peripheral task started, blink task started. So if we flick over, you can see that that's flashing very slowly, which means we've got a connection. And you can probably see the same in the robot if I hold that up, and you can see, let's see if you can catch that. You can probably just about see there the white cable. There's like a little streak of light. That's the Pico inside the robot doing the same thing. So I'm just going to move that there. So it says connected on the screen because we are actually connected. And you can see there, connection from device, address public, and then there's actually a MAC address, and we're connected, which is cool. So if I now press a button such as forwards, you can see on the console it says button up, press down, button up has been released. And you could see that our robot also moved. If I press down, you can see our robot's shot off there as well, and button down, pressed, button released. So what's cool is we can do things like, if I disconnect the power from our robot, I'm going to try and do this at the same time. I want you to watch the screen. So if I disconnect the power from the robot, the screen on our remote says disconnected, and you can see on the console that it also says disconnected. Let's put the power back into our robot, and let's see what happens on the screen. It says connected, and you can see connection from device. So we've got really robust code for connecting and disconnecting from our robot should anything actually happen. So how cool is that? That was worth coding until 2 AM in the morning. It's really fast to connect, really robust at handling disconnections, and it just works. And if we get the both of these running on batteries, we've got like a true wireless Bluetooth and battery powered solution. Really love that. Okay, let's get back to our slides. So yes, I did mention I go live every single Sunday at 7 o'clock, so if you want to join me, you can do for the chat after the show. And if you want to get yourselves one of these gamepads, you can buy one. They are £6 to buy, which is an absolute steal. I'm not providing the Picos, the buttons, or the OLED displays. You can buy them yourselves very cheaply, probably locally. But the PCB, I got these manufactured by PCB Way, but I pay for them myself, so they're not sponsoring today's show. This is all from my own bank, if you like. You can also get yourself the Robot Maker's Almanac if you want to get all the pinouts for the Pico, for example, or tack buttons, whatever you wish. That's all that kind of information is inside here. So there's a microbit, for example. Just seen a microbit on my desk, actually. That's for that little BBC microbit, and we've got all kinds of other things in there. So there's a Raspberry Pi, for example, as well. We also have the maker notes. We've got quite a few of these in store as well. Might need to print some more of these, and these are great for sort of sketching down your ideas. I think I used this the other day to sketch down. What was it? I can't remember what on earth that is. But there's my sketch. I don't know if you can see that. I'll put it on the other camera. As you can see, I was using that to sketch out some ideas and some measurements. I've absolutely no idea what that is now. Anyway, there's my maker notes that I actually use myself. So you can head over to kesrobots.com and you'll find all the links at the top of the page there to purchase any of these things. They all help support the show, so if you're looking to get one of these, it's just price of the shipping extra you'll need to pay. If you want to join our Discord server, we have a really great community over on Discord. You can even share pictures of projects that you're working on, ask questions if you get stuck on any code, and you can also share pictures of your pets as well, such as our little Mini. And if you want to follow me on social media, I'm on all the social medias. I'm on Threads at KevMcAleer at threads.net. I'm on TikTok at KevMcAleer6. I'm on Instagram at KevMcAleer. I'm on X at KevsMac. I'm on Mastodon at KevsMac at Mastodon.social. And I'm also on Blue Sky at KevsMac.bsky.social as well. You'll see all kinds of behind the scenes stuff on there. And if you want to follow me and help support the channel, you can get your name in the credits simply by going over to kesrobots.com/coffee. You can also join the Buy Me a Coffee membership. Excuse me, or alternatively, you can join the YouTube membership program as well. Sorry about that, I'm running out of breath there. So let's have a look at some of the people who have done exactly that. So over here on the left hand side we have V Wilcox, who bought me a coffee. Thank you very much for that. We have Coding Marie, who bought me a coffee as well. Thank you, Marie, for that. And we have Doug Toppin, who bought me 3 coffees. Thank you for that, Doug. We also have the members of our Buy Me a Coffee. We've got Marie TKD, we have Andrew, we've got Shemi, we've got Jeff, we've got Dean Corty, Marlene, and we have Tom. And today's show is actually dedicated to Jeff because he actually asked me about the remote control and do I have any code that I could share on that. So all that is now live on kesrobots.com. On the YouTube membership side, we've got Khan, we've got Dale from Hybrid Robotics, we've got Marie, we've got Michael, Steve, Ford, Bello, Oxrad, Littleback, Paul, Johnny, Prem Kumar, Stephen, John Paul, Alistair, Cassie, Tinkering Rocks, Johnny Bates, and we have, of course, Tom as well. So thank you so much for supporting the show. Can't tell you how much that means to me that you continue to support the show. And what that little spinning logo there tells me is that this is the point in the video where YouTube will recommend a video over here for you to watch next from the video catalogue of over 400 videos that I've created to date, all on Raspberry Pi Picos, MicroPython, Robotics, PCB manufacture, all kinds of stuff like that, home automations, Internet of Things. So definitely check one of those out. And it's at this point in the show, if you're watching this on replay, I'll say thank you so much for watching, and I shall see you next time.